Alright, welcome back here to the second part of the video. Now what I want to say though is that first video really focused on finite geometric series, right? Finite meaning that they had a limited amount of terms. Well, I'm not going to go into the whole thing right here, but there is such a thing as an infinite geometric series, right? And so here it is, right? So if I even take a look at one that I was looking at earlier, maybe this is the pattern, right? And before, it had a number that told me that it was actually finishing, but here it looks like it's just stopping, right? So if this goes on forever, that's what it means when the three dots are at the very end of the series. What is going to happen to the sum? Am I going to be able to find it, right? So there's two different types of infinite geometric series here. All right, there is a geometric series an infinite geometric series, excuse me. There's two types of infinite geometric series when R, or the absolute value of R, is greater than 1, right? So some examples of that might be -3, +4, any number that's basically to the left of -1 on the number line or the right of +1 on the number line. Okay, that's what I'm trying to say with this right here, right? What happens with that is the sum actually diverges. The sum diverges. I'll tell you what that means here in just a second. Okay? But let's get back to the other part. So the other thing that an infinite geometric series can happen here is if the R, or the absolute value of R, is less than 1. Then, excuse me, then the sum converges. Okay? So here's an idea of this. Let me show you something that really doesn't have any kind of idea that to do with these series, but maybe to help explain what this word converge and diverges look like. Alright, let me just draw what you might assume to be just a the old X and Y axes, right? The old Cartesian coordinate plane. And let's say that I want to see what happens on this graph as two different pictures over time and as it relates to this purple line. Okay? So I'll do one here in blue. This one on the left, it's going to start right here, but then it just takes off. And the further that we go on this trip from left to right, the blue line gets further and further away from my purple line. Okay? Another way that I can express this is something like this. It might start far away, but as I move, come on, red pen. As I move over time, this red line is running out of ink, but more importantly for our sake is it gets closer and closer to this purple line. This one is what we call converges. Come on, purple, or come on, red. This is what we call converges, right? Where it's getting closer and closer. Think about that. That's like a decay right there, right? So if you recall back to a little bit earlier, obviously before this e-learning process has started, that's a decay process, right? That's when the number in front of the exponent, the R in this case, was less than 1. This convergent right here, I know this blue pen works better than the red. This converges right here for the blue line. This is an exponential growth. This is what happens when r is bigger than 1, or the number in front of the exponent is bigger than 1. All right? So what happens here is we are only going to talk about diverges, okay? At least for today. We're going to come back next week and we'll talk more about some others. But diverges, that's what happens when we just have this idea right here, okay? There is no sum to an infinite geometric series that diverges. Okay, there is for it converges, but we're not going to talk about that here. All right, so if you see an infinite series, just say, does it converge or diverge? That's a good question to ask yourself. If it diverges, there is no sum.